Black holes are those mysterious objects in space that suck everything around them, including light. But did you know that nothing ever really seems to enter a black hole? Let's say you have an enemy, and in a bold move, you decide to put them in a rocket and launch it towards a black hole. As they get closer, you expect them to speed up, right? After all, the gravity there is immense. But what you see is the exact opposite. The rocket seems to be slowing down. And why does this happen? From your point of view, their time is slowing down. It's as if they are stuck in a slow-motion video. At the moment, they should cross the event horizon, that point of no return where not even light escapes. They don't disappear. Instead, they and the rocket seem to freeze in time. The rocket's light gets dimmer and redder until it completely vanishes from view. Albert Einstein, a true genius with hair that only gets cooler over time, discovered that gravity is not a direct force between masses. Instead, objects like the sun curve the space-time around them. Imagine space-time as a trampoline and the sun as a heavy ball sinking in the middle. Other objects, like Earth, roll along this curvature, resulting in their orbits. Now, let's talk about black holes, those cosmic monsters that devour everything around them. The first solution to Einstein's equations predicted not only black holes but also their opposites, white holes. These equations suggest the existence of parallel universes and, who knows, maybe even a way to travel between them. But before going too far, let's talk about wormholes. Have you ever thought about traveling from one point in the universe to another in the blink of an eye? Wormholes are theoretical shortcuts in space-time that could make this possible. Imagine you have an equation that, on one side, asks about the distribution of matter and energy in the universe. On the other side, this equation tells us how this distribution curves space-time. It sounds simple, but this simplicity hides daunting complexity. We are dealing with a family of coupled differential equations, which means solving it is like solving a three-dimensional puzzle in motion. To visualize a solution to these equations, think of floating in empty space. Suddenly, a flash of light appears above your head and spreads in all directions. From that moment, your entire future will happen within that bubble of light because nothing can escape it unless it travels faster than light. In a two-dimensional diagram, this bubble would be a growing circle. Now, if we record time passing and take regular photos, this bubble would turn into a cone of light, the famous future light cone. In 1915, in the middle of World War I, Einstein published his equations, but he couldn't find an exact solution himself. And that's where Carl Schwarzschild comes in, an astrophysicist who, even on the battlefield, managed to solve the problem. Schwarzschild simplified the problem by imagining a universe with a single point mass, spherical and non-rotating. Using spherical coordinates, he found the first exact solution to Einstein's equations, known as the Schwarzschild metric. This solution showed that far from the mass, space-time is nearly flat, but as you get closer, it curves more and more, affecting everything around it, and even the flow of time. Einstein was amazed by this discovery, but soon problems arose. At the center of the mass, the equations explode to infinity, a singularity. And outside the center, at the so-called Schwarzschild radius, we find another singularity where space-time curvature is so extreme that nothing, not even light, can escape, the concept of a black hole. What happens when a star reaches the end of its life? During most of a star's life, there is a balance between the gravitational force pulling everything inward and the radiation pressure pushing outward, thanks to the energy generated by nuclear fusion. But what happens when the star's fuel runs out and this radiation pressure decreases? Gravity starts pulling all the star's material inward. In 1926, Ralph Fowler suggested a possible mechanism. The Pauli exclusion principle states that fermions, like electrons, cannot occupy the same state. This means that the more a star is compressed, the faster the electrons move, creating an outward pressure known as electron degeneracy pressure, which would prevent the star from collapsing completely. it would become a white dwarf with much higher density than a normal star. 4 years later, a young 19-year-old scientist named Subramanian Chandrasekhar realized something alarming. Electron degeneracy pressure has its limits. Electrons can move faster and faster, but they can't exceed the speed of light. This means this effect can only support stars up to a certain mass, known as the Chandrasekhar limit. And beyond that limit, even electron degeneracy pressure couldn't stop a star from collapsing. When a star collapses beyond the white dwarf stage, electrons and protons merge to form neutrinos and neutrons. These neutrons, being fermions with almost 2,000 times the mass of an electron, create an even stronger degeneracy pressure, supporting neutron stars. In 1930, J. Robert Oppenheimer and George Volkoff discovered that even neutron stars have a maximum mass. Shortly thereafter, Oppenheimer and Hartland Snyder showed that for heavier stars, nothing could save them when their fuel runs out. They wrote, "This contraction will continue indefinitely." Oppenheimer offered an interesting solution. He said that to an outside observer, it would seem like nothing ever crosses the event horizon of a black hole. However, if you were traveling into it, you wouldn't notice anything unusual and would continue your journey normally. How can this be? Imagine the event horizon as an imaginary line around the black hole. For someone observing from the outside, any object approaching this line seems to slow down more and more as it gets closer, as if moving in slow motion. This happens because, from the external observer's point of view, the object's time is almost stopping. On the other hand, for someone inside the rocket, everything seems normal. Time passes the same as always, and the person doesn't notice anything strange when crossing the event horizon. This occurs because time and space are extremely distorted by the intense gravity of the black hole. Light, which normally travels in a straight line, is curved by the black hole's gravity. When light tries to escape from near the event horizon, it is pulled back, making it increasingly difficult for it to get out. From afar, it looks like the light is trapped and never fully escapes, creating the illusion that nothing crosses the horizon. Let's talk about a specific point in this scenario, the Einstein-Rosen bridge. To visualize this, we need to change coordinates. This line that appears is a constant Kruskal timeline, connecting the spaces of two different universes. You can see space-time following this line, going from right to left. When we are far from the event horizon, space-time is nearly flat. But as we get closer, it starts to curve more and more. At the crossing, we are at the event horizon, and if we go through it, we end up in a parallel universe. It seems like a wormhole, doesn't it? Hypothetically, we could use a black hole to travel from one universe to another. Hypothetically, because these wormholes are not stable in time. Imagine a bridge that stretches and shortens constantly. If you try to cross it, at some point, it will become too short. You run and run, but the bridge stretches, and you never reach the other side. This rapid closure prevents anything from crossing. This is evident in the Penrose diagram, where one universe does not have a light cone that allows travel to the other. The only solution would be to travel faster than light. Is there another way? The Schwarzschild solution describes a non-rotating black hole. But all stars rotate, so black holes must also rotate. After Einstein's equations were published, Schwarzschild found his solution in weeks. However, solving these equations for a rotating mass proved to be a huge challenge. Physicists tried for decades until, in 1963, Roy Kerr found the solution for a rotating black hole. This changed everything. A rotating black hole has several layers and is no longer spherically symmetric. The rotation causes a bulge at the equator, making it symmetric only around its axis of rotation. Around this rotating black hole, space is dragged along with it, and you are also dragged. As you get closer, space spins faster and faster until it exceeds the speed of light. You enter the ergosphere, a region where it is impossible to stand still. You can still escape, but you need to fight against the dragging space. Closer in, you cross the outer horizon, the point of no return. Here, you can only go inward, but suddenly, something unexpected happens. You enter a new region where you can move freely again without being doomed to the singularity. This is the inner horizon, where physics gets even stranger. In a normal black hole, we have a singularity point. But in a rotating black hole, this singularity expands and forms a ring where space-time does very strange things. In the case of the Kerr solution, an immortal astronaut could send light into the black hole, accumulating energy along the inner horizon, creating a new singularity. This means white holes, wormholes, and other universes would disappear. In 1987, Michael Morris and Kip Thorne analyzed wormholes that could be used for interstellar travel. They found geometries allowed by Einstein's general relativity that could connect different parts of the universe or even distinct universes. The problem? These geometries require exotic matter with negative energy density, something that goes against the laws of physics. Therefore, although mathematically possible, wormholes and parallel universes may not exist in practice. Still, we used to think black holes didn't exist, and now we know they are out there. Who knows what else we might discover? Remember to subscribe to the channel and tell us what you think. Do wormholes and parallel universes exist or not?